So we have already seen what it means for two vector spaces V and W to be isomorphic to each other. We have developed the notion of an invertible linear transformation. In this video, we will explore how a linear transformation being invertible reflects upon the matrix associated to it. So we begin by recalling the definition of an invertible matrix. Let's start by a recollection. Definition. So let A be an M cross N matrix. We say that a matrix B matrix, or rather an N cross M matrix B is the inverse of F of A if AB is the identity matrix of size M and BA is the identity matrix of size N. So A is an M cross N matrix, B is an N cross M matrix. So if you look at the product of these matrices AB, it will just turn out to be an M cross M matrix, and we demand that that matrix be the identity matrix. Similarly, BA is demanded to be the identity matrix of size N. So we say that the matrix B is then an inverse, is the inverse of the matrix A. So we then say that A is an invertible matrix. So an immediate exercise which will follow this is to prove that the matrix A has a unique inverse. So the techniques to prove have been developed and used many times. So you should also use the theorem which was proved in the last video, wherein we showed that matrix multiplication was or is associative. So the exercise is to show that the inverse of a matrix A is unique. So start off with two potential inverses B and B prime and prove that B is equal to B prime. Alright, so why did we talk about an invertible matrix to begin with? So as is to be expected, our goal would be to show that an invertible linear transformation has an invertible matrix associated to it. So we will come to that. Before that, let me just for the sake of completion, let me give an example. So let A be a matrix given by 1, 2, 3 in the diagonals. Let me make my life easy here. Then A inverse is equal to 1, 0, 0, 0, 1 by 2, 0, 0, 0, 1 by 3. Right. So this is a familiar concept for you, most probably from your high school. So let me not spend too many, let's spend time on too many examples. Let me directly jump into the theorem here, which essentially captures the relationship between invertible linear transformations and invertible matrices. So let T from V to W be a linear transformation between finite dimensional vector spaces. V and W. Let's fix an ordered basis alpha and beta of V and W. Suppose alpha and beta are finite, that's already redundant, it's already known to be finite, ordered basis of V and W respectively. Then the theorem states that T is an invertible linear transformation if and only if the matrix associated to T with respect to beta, alpha and beta is an invertible matrix. So, if and only if the matrix T, so alpha beta, is an invertible matrix. Not just this, we exactly know what the inverse of this matrix is. Moreover, the inverse of alpha beta, the inverse of this matrix, this just turns out to be the matrix associated to the inverse of T, the inverse linear transformation of T. So, this is just the matrix of T inverse. Now, recall that T inverse will now be a map from W to V, and therefore, this will be beta alpha. So, we exactly know what the inverse of our matrix corresponding to this particular linear transformation is. So, let us give a proof of this statement. So, we are given alpha and beta. So, let us once and for all in the context of this proof, let alpha be equal to say V1 to Vn and beta be equal to W1 to Wm be ordered basis of V and W respectively. Alright, so let us see what our goal is. So, let us first assume that T is an invertible linear transformation, the one I am underlining in green, and let us prove that the matrix associated to T is an invertible matrix. Okay, so let T be an invertible linear transformation. What does it mean to say that a linear transformation is invertible? It means that then there exists an inverse, and we know that the inverse is unique. So, and suppose T inverse from W to V be its inverse. What do we know about this inverse? When composed with T, it gives us identity on both sides. So, if you look at T inverse, then T inverse is just the identity map of W, and similarly T inverse T is just the identity of V by the very definition. We also know that the identity map of W, so we know, so okay, let us see what is T inverse from beta alpha. So, recall that T inverse is a map from W to itself, and sorry, so it will not be beta alpha, it will be beta, but this is just the matrix of the identity map with respect to the basis beta, and we know what that particular matrix is. The matrix of the identity with respect to beta will just turn out to be the M cross M identity matrix. We also have already seen how the matrix corresponding to the linear transformations behave under composition. So, let me just note that down. Recall that T inverse beta is equal to T inverse from beta to alpha and T from alpha to beta. And therefore, we have T alpha beta times T inverse beta alpha is equal to the identity matrix of M, identity matrix of size M. A similar argument, let me just note it, a similar argument tells us, gives us that T inverse beta alpha T alpha beta is the identity matrix of size n, because T inverse T will just turn out to be the identity map of the vector space V, and with this will hence tell us, and therefore the matrix T alpha beta is invertible. What is the inverse? With inverse T alpha beta inverse being equal to the inverse of the matrix of the inverse from star. This is from star. Alright, so we have proved one half of the theorem, which states that if T is an invertible linear transformation, then the matrix associated to T with respect to alpha beta is invertible. Moreover, if T alpha beta is the matrix, the inverse of that matrix will be the matrix of the inverse corresponding to beta alpha. Okay, so now let us prove the other direction. So what is the other direction? The other direction demands that if you start off with an invertible M cross N matrix corresponding to a linear transformation, then the matrix, the linear transformation is also an invertible linear transformation. Okay, so let T alpha beta be the matrix of T, of course this is the matrix of T with respect to alpha beta. Let me not write that again and again. Let this matrix be an invertible matrix with inverse given by B. So let us give some name to alpha, or rather the vectors. Let us list down the vectors in the ordered basis alpha and beta. So let alpha be, recall that alpha is an ordered basis of V which has dimension n, and let V1, V2 up to Vn correspond to the vectors in the ordered basis alpha, and beta similarly be some W1, 2, recall that W is of dimension m, so this will be some list of m vectors. So let alpha and beta be ordered basis of V and W consisting of V1 to Vn as the vectors in alpha and W1 to Wm as the vectors in beta. And we know that there is an inverse to the given matrix associated to T corresponding to this these bases. So let us see what the entries of this matrix is. So let B be equal to something like B11. So where is what is B? B is the inverse of the matrix associated to T, which is going to be an M cross N matrix. So this is going to be an N cross M matrix. This is going to be N1, Nm. Right. Now let us define a function. So define a function S from W to V in the following manner. We will invoke one of the theorems we have proved in one of the previous videos, namely which says that if you are given a basis of the domain, in this case W, and say basis consisting of say w1, w2 up to wm, and suppose you are given vectors say x1, x2, or rather v is already used, u1, u2 up to um, then there exists a unique linear transformation which maps wi to ui. So let's use that to define this particular map S by defining what S is on a basis of W. So recall that to define a linear transformation on W, linear transformation from W to V, it is enough to describe the function S on a basis of W. But we are already given a basis of W. So consider S of Wj. This is how we would like to go about defining our linear map S. But what would Swj be when we know that the matrix of S should be B? So that is our goal, right? So we would like to somehow construct an inverse of T. Now what is the information we have? The information we have is the inverse of the matrix corresponding to T. And we are already familiar with what the matrix of this inverse should be. It will be the inverse of the matrix. So our expectation should be that the matrix of S should be B corresponding to beta alpha. And if that is to be the case, let's see what Swj should be. Let me show you what B is on the top, and let me define Swj by keeping B above. So this will just turn out to be equal to B1j V1 plus B2j V2 plus Bnj Vj, which let's call it as Uj. By one of those theorems which we proved earlier, then there exists a unique linear transformation S from W to V, so let's call this Uj, such that Swj is equal to Uj. My claim now is that this linear transformation S is the inverse of T. So how do we go about proving that? So let us see what the matrix corresponding to TS is. So consider TS with respect to beta alpha. So we know that TS is now a map linear transformation from W to itself. So this is not beta alpha, this is beta beta. And we know that this is the composition of two linear transformations. So this will be S beta alpha to the right and T alpha beta. And we know that this is equal to T alpha beta times B, which you should go back and check by the very definition of our S here. The matrix of S turns out to be B, right? So this is equal to T alpha beta times B. But what was B? B was exactly the inverse of our matrix T alpha beta, which is just equal to the identity map of size M. But we know some linear transformation which gives us this particular matrix, which is just going to be equal to the identity map from W to itself corresponding to beta. So from here it's straightforward to check that TS is equal to IW. So it's an exercise for you to see that this is equal on each of the basis vectors, and therefore by the that's just straightforward. I wouldn't want to call it an exercise, but nevertheless you should check this particular arrow carefully. Similarly, we will be able to conclude that ST is equal to IV, and therefore S is the inverse of T, which gives T is an invertible linear transformation. That completes our proof. Alright, so now given a matrix A, there is a very natural linear transformation which can be associated to it, namely LA. So this theorem tells us that A is an inverter. So let me write it down as a corollary. So let A be an M cross N matrix. Then A is invertible if and only if LA is invertible. Not just that, we know more, we know exactly how or what LA is. Also, LA inverse, the inverse of the linear transformation LA will be the linear transformation corresponding to A inverse. Okay, so the proof is just a direct application. It's a corollary, it's a direct application of the previous theorem. So the first part is fairly straightforward. Notice that with respect, so it's just finally boiling down to the choice of the right basis. So let alpha and beta be the standard basis of Rn and Rm respectively, and just boils down to checking that with respect to the standard basis, the matrix of LA is just A, and the previous theorem tells us that LA inverse, LA alpha beta the whole inverse, the matrix inverse, which is equal to A inverse, this is equal to LA inverse beta alpha by our theorem which we have just proved. But we also know that A inverse is the matrix of the linear transformation corresponding to A inverse, but let me write it down. LA inverse with respect to say beta alpha is nothing but A inverse, and therefore LA inverse beta alpha is equal to the matrix of the inverse of the linear transformation LA with respect to beta alpha, and from there again on the basis it's equal, and therefore it will be equal everywhere, and that establishes the corollary. Another corollary is that, so let me just note it down. Another corollary states that if A is an M cross N, it's a corollary to this corollary which states that if A is an invertible M cross N matrix, then M is necessarily equal to N. So let's see how that is. So let A be an invertible M cross N matrix, then M is equal to N. So by the previous theorem, so let's look at a proof. By the previous theorem, A is invertible, is an invertible matrix if and only if LA, so where is LA from? LA is a map from Rn to Rm. So LA is an invertible linear transformation. Now, what do we know about isomorphic vector spaces? So we know that two vector spaces are isomorphic, or in other words, there exists an invertible linear transformation between them if and only if their dimensions are the same. So which we have proved in one of the videos in this week. This is if and only if dimension of Rn, which is equal to n, so dimension of Rn is equal to dimension of Rm. But what is dimension of Rn? That is n, and what is dimension of Rm? That is m, and therefore this is if and only if n is equal to m. So A is an invertible linear transformation. Okay, so there is a slight error which one should be very careful about. So this will tell us that dimension of Rn is equal to dimension of Rm. It's not an if and only if statement. You could have LA, which is not necessarily an invertible linear transformation, even though the domain and the range are Rn. So for example, look at the map LA corresponding to the 0 matrix. That will not be an invertible linear transformation. So this direction of the implication here, which I am now circling in green, one should be very careful. I had written an if and only if there, which is not the case. Right. So this implies that dimension of Rn is equal to dimension of Rm, which is if and only if n is equal to m. So we have effectively shown that if A is an invertible m cross n matrix, then n is necessarily equal to m. Alright, so in the proof of the theorem which we proved just now, the theorem which stated that if T, or rather T is an invertible linear transformation if and only if the matrix associated to T is invertible, we used an argument to construct a specific inverse linear transformation of T. We shall use that style of construction to prove that the vector space of all linear transformations between V and W, which we had seen earlier and we had given a name L of V comma W, that is isomorphic to all m cross n matrices over R. So that is the next theorem that we will be proving. So recall that L of V comma W denoted the vector space of all linear transformations from V to W. So this theorem tells us that L of VW is isomorphic to the matrices of size m cross n when V and W are respectively of dimension m and n. So let's see what the statement is. So let V and W be finite dimensional vector spaces. Suppose the dimension of V is equal to n and the dimension of W is equal to m. So let dimension of V is equal to n and dimension of W be equal to m. Then the theorem states that L of V comma W is isomorphic to the matrices over R of size m cross n. Okay, let's give a proof of this. The proof is quite straightforward. We have seen the idea that is being used in this proof just a few minutes back, so it's just going to be a imitation of that. So let's start by fixing an ordered basis. So let alpha be equal to v1 to vn and beta equal to w1 to wm be a basis, be basis of v and w respectively. Let's now define a map phi. So define capital phi from L of VW into the M cross N matrices over R. So recall that M cross N matrices over R was a vector space consisting of all M cross N matrices, and it was having a basis with all the matrices with 1 in say ij and 0 elsewhere. So there will be mn of them. So the dimension of the vector space on the right is actually mn. So let's define a map phi from L of VW into M cross N over R by what you should be expecting. Phi of linear transformation T is just going to be the matrix of T responding to alpha beta. So we have seen that phi is a linear transformation. In another guise, we have already seen it. Let's check that phi is a linear transformation. So see that phi of S plus T is just going to be equal to the matrix of S plus T alpha beta, and we have already seen that this is equal to S alpha beta plus T alpha beta, which is equal to phi of S plus phi of T. And similarly, the scalar multiple, so this is for all S and T in L of VW. And similarly, phi of C times T is nothing but C times phi of T for all T in L of VW and C in the scalars. So what is phi of Ct? It is going to be the matrix of Ct with respect to alpha and beta, which is going to be C times the matrix of T with respect to alpha and beta, which is nothing but C times phi T. So we have seen these two in the first video of this week. So what we have done just now is to establish that our map phi, which we just defined, is a linear transformation from L of VW into the M cross N matrices over R. So what remains to show is that it is an isomorphism. So invoking another result which we have already shown, we will prove that phi is both injective and surjective, and thereby proving that an injective and a surjective linear transformation is an invertible linear transformation. You will use that result to prove that phi is then an invertible linear transformation. Okay, so the injectivity comes by noting that so this I will leave it as an exercise for you to check that the null space of phi is necessarily the 0 linear transformation. Is the 0. So this is the 0 linear transformation. Just notice what the matrix corresponding to phi will turn out to be if the linear transformation is being mapped to the 0 vector, 0 matrix. It will just be the matrix with 0 entries, which means that every basis vector is being sent to the 0 vector, and therefore the linear transformation is the 0 linear transformation. So this particular exercise establishes that Phi is injective. Notice that we have already shown that phi is a linear transformation, and this tells us that phi is injective. And how about surjectivity? So surjectivity. Let's now next do surjectivity. So let's take some arbitrary m cross n matrix. So let A be an m cross n matrix. We have seen this technique. This is what I was talking about a few minutes back. So let A be the matrix given by these entries. And did we give what the vectors? Yes. So V1 to Vn and W1 to Wm are the vectors in the ordered basis corresponding to alpha and beta. So let's define a map T from V to W where T Vj will just turn out to be equal to A1j W1 plus A2j W2 plus Anj or rather Mj Wm. So check that the matrix of T corresponding to alpha beta. Okay, so wait, before that I just defined what T is on the basis vectors alpha, and by one of the theorems we have proved earlier, there exists a unique linear transformation which maps each of the Vj's to the vector which I have just put in the bracket. Let's call it Uj. So there exists a unique linear transformation. There exists a unique linear transformation by one of the theorems proved earlier. Unique linear transformation T which maps. So notice that here I have only defined T for the basis elements V1, V2 up to Vn, and with that there exists a unique linear transformation T from V to W such that T of Vj is equal to A1j W1 plus Amj Wm. And what is the matrix of T with respect to alpha beta? Check that this is equal to A. But what does it mean to say that the matrix of T with respect to alpha beta is A? It means that i.e. phi of T is equal to A. That shows that our map phi is surjective. So we have shown both injectivity and surjectivity. Thus, phi is an isomorphism. So what we have essentially shown, it's a very powerful result. Let me just show you the result once more. This theorem tells us that the vector space of all linear transformations from V to W is isomorphic to the m cross n matrices over R. And as a corollary, so let's stop with the corollary, which is a direct consequence of the theorem. It tells us what the dimension of L of VW is. Dimension of L of V comma W, remember that two matrices are isomorphic if and only if the dimensions are the same. So this is nothing but dimension of the m cross n matrices over R, which is equal to m times n. So this has already proved the result. Corollary states that the dimension of L of VW is m. Okay, let me stop here.